L-commit. So this problem is about creating and proving a commitment protocol. So before we begin, let's go over some motivation. When exactly would you need a commitment protocol? So let's go over a little setup, and as usual, we're going to have our main players, Alice and Bob. So in this setup, Alice is going to be thinking of either heads or tails, and Bob is going to try and guess. So let's say he guesses heads, and then Alice is going to confirm whether or not he won and got it right. And she says, nope, actually it was tails. So do you notice anything kind of fishy about this game? Imagine playing this with your sibling, it would get pretty boring pretty fast. The problem here is that we can't really tell if Alice was lying. Maybe she really was thinking of tails and Bob lost, but maybe she was thinking of heads, and after Bob gave his guess, she changed and said, nope, I was actually thinking of tails. What we really want is a way for Alice to commit to a value before Bob does his guess. So you can imagine she writes down tails on a piece of paper so that after Bob does his guess, we can confirm that, yep, her original choice was tails. At the same time, though, she can't just leave this paper lying around. If Bob could see it, then he could always guess correctly, and that messes up the game too. So she needs a way to commit to it, but also lock down this commitment so that Bob can't see it. But it can't be permanently locked. She needs to have the key and later be able to unlock it and prove to Bob that her original answer was tails. So that's the setup for how a commitment protocol would work. Let's formalize this a little bit. So the main steps in this procedure are step 1, Alice commits to a value. In our little play example, the value she committed to was either heads or tails, but as we saw previously in all these different cryptography protocols, normally the value we're picking from is going to be from the universe Z star P, where P is a prime number. Step 2 is that later, Alice can choose to reveal the value that she picked. So in our little play example, she was able to reveal the value after Bob gave his guess. In general, she just needs to be able to reveal after some time. And the final step, step 3, is that Bob can confirm that she didn't cheat, i.e. she didn't change her M value between committing and revealing. So there's some things we need to guarantee through these 3 steps. So the things we need to guarantee are binding and hiding. Binding just means exactly this step, that Alice can't change the value M that she committed to. And hiding means that Bob can't learn anything about M before Alice does the reveal. So with those 2 things in mind, let's try and formalize this commitment scheme and see exactly how it works. For some setup, we're going to need to fix our Z star P universe, and as we saw in the notes, we always know that there's a generator for Z star P. So let's say that we've got this public generator G, so both Bob and Alice have access to this generator G. And as a reminder, what does it mean to be a generator? A generator just means that when you take the powers of this generator G, in other words, G to the I, where I comes from Z phi P, this set right here covers all of Z star P. So you can generate every single value from Z star P using the generator powers of G. Okay, so now let's get started with the protocol. So the first thing Alice is going to do is she's going to pick her value M from Z star P, and everything that she's doing in this box is hidden from Bob. So this is the value that she doesn't want to reveal just yet. So how is she going to commit to this value? In other words, this is akin to her writing down the word tails on the piece of paper and putting it in a locked box. The way she's going to do that is she's going to pick some exponent values R and S from Z phi P, and then she's going to calculate powers of the generator with these exponents R and S. Specifically, she's going to calculate A equal to G to the R and B equal to G to the S. And finally, she's going to hide her value M. This is kind of like putting it in a locked box by calculating this value V equal to M times G to the RS. After she's done calculating all of this stuff, she's going to send over to Bob A, B, and V. This is step 1. This is Alice committing to the value M. Later, in our little play example, later would be after Bob announces his guess, Alice can choose to reveal M. The way she's going to do the reveal is by sending over the values R and S. After these 2 steps are done, now Bob can go ahead and confirm that she didn't lie and the value that she revealed is in fact the value that she committed to. And the way Bob is going to do this confirmation in step 3 is he's going to confirm that her A and B were legit, so that now that Bob has access from step 2 to R and S, and he always had access to the public generator G, he himself can calculate G to the R and G to the S and confirm that that was in fact what the A and B that Alice sent in the first step. After he does this confirmation, he can go ahead and see the revealed M. And the way he can see the revealed M is by calculating G to the RS, because he has R, S, and G. And by virtue of the way that V was constructed, we can go ahead and get M from this once we have G to the RS. So because G is a generator, we can easily get the inverse for g to the rs, multiply that by v, so v times the inverse of g to the rs, and that is going to be equal to m just based on the way v was constructed, so now Bob has the revealed value of m. So that's the entire setup for the protocol, and the question becomes, is it actually binding and is it actually hiding? Let's tackle binding first. Is it possible for Alice to change her value? In other words, after she picks the value m and she commits through it in step 1, is it possible for Alice to trick Bob, and when he does the reveal, when she does the reveal, Bob actually thinks that her value was not m, but some other m prime? So in other words, Bob does the confirmation, and he checks that a is equal to g to the r, and he checks that b is equal to g to the s, but somehow, when he does the reveal, he calculates some other value instead of m, he gets some other value m prime. Could this scenario ever happen? Well, once Alice has committed, really the only leeway she has in order to kind of lie and trick Bob is in step 2 when she's sending over this r and this s. So is it possible for Alice to pick some sneaky r prime and s prime? So if she sends that, if she sends over some r prime and s prime, can she find some values that pass the check so that g to the r prime would pass the check for a and g to the s prime would pass the check for b? But when Bob does these calculations and he does g to the r prime and s prime, and then again calculating m, he does r prime and s prime, is it possible here that she picks some other r prime and some other s prime that aren't equal to the original r and s so that Bob ends up with m prime? So take a moment and think if she would be able to do this and still pass the checks. And the answer is no. So no, she won't be able to do this. And the really important part is, why can't she do this? And this has to do with the fact that G is a generator for Z star P. So recall the definition of a generator. And also note that the size of Z star P is exactly phi of P. So in other words, we know that for all of the different exponent that I could be, in other words, all the different values that we picked for R and S, they come from Z phi P. The GIs must be distinct. If they weren't distinct, you wouldn't be able to generate everything from Z star P. And since they're distinct, that's another way of saying that there is no possible R prime and S prime for Alice to pick. There's no R prime that's going to work out and have G to the R prime be A. She has to send the correct R in order to get A. And similarly for S prime. So since she has to send over the correct R and S in order for these checks to pass, that means that this entire scheme is binding. Awesome, so now let's work on hiding. So this is asking the question, is it possible for Bob to peek at the value of m before Alice does the reveal? So before Alice does the reveal, before she does step 2, can Bob use the information that he already has to figure out something about m? So the information he already has is just a, b, and v. So using a, b, and v, can Bob get m? And recall that under the hood, Bob doesn't know the values of r and s, but under the hood, a and b are really g to the r and g to the s. And his goal is to get m using this. And we already know that you can extract m if you can somehow get g to the rs. So the question then just becomes, can you get g to the rs just using g to the r and g to the s? So take a second and recall what we did in the Diffie-Hellman strategy. And of course the answer to this is also going to be no. So we assume, because we're using the decisional Diffie-Hellman assumption, aka DDH, under this assumption, it says that no, Bob can't get g to the rs just using g to the r and g to the s. There are some caveats to this, so you can check out the notes, but in general, we just assume that he won't be able to get the value of m via getting the value of g to the rs if he's only given g to the r and g to the s. So in other words, this scheme is also hiding, and thus we've proven everything we needed to know for to show that this commitment protocol works, and that is it for LCommit.